But the problem is, while we were in lockdown, I really wanted to understand this virus, but how do you research a disease that doesn't have any data on it yet, right? This epidemic just came out. No one really had any data. What do you do in order to say, well, you want to know more about this particular disease, but there's nothing out there. So what we did was we found something related. And actually, there were two epidemics before the current one, very similar coronaviruses. One was SARS, which happened in about 2002. It affected mostly Asia. Very severe, which is why it didn't spread worldwide. And then there was another one, Middle East respiratory syndrome, or MERS. This was more in the Middle East, about 2012. Again, very, very severe. Hence the reason why it probably didn't spread as well. And then again, the one we really want to understand is the COVID-19. So again, this was the SARS-CoV-2 virus. So we've got this potential other diseases out there, previous diseases, epidemics, kind of look like our virus. Maybe we can use that. And when we actually look at the sequence, these are particular domains on these different coronaviruses. Again, here's the current or the SARS-CoV-2, SARS-CoV, and then the MERS. And what you find is when we compared the CoV-2 to just CoV, there's about 80% homology between these diseases, which is, for a virus, that's a lot of similarity. So we thought, well, that's a good sign. Maybe we can use this. What's also interesting is that has some of the same hosts, both bats, and most importantly, it binds the same receptor. MERS does not. It uses a different cellular receptor for entry. Both these viruses use the ACE2 receptor, similar symptoms. And what they found is actually the SARS-CoV that came out in 2002. Again, I mentioned that it was more severe, which actually kind of works better for us, right? That I don't really care about a mild form of SARS-CoV-2. I want some, what we're really interested in is finding the severe form to potentially have therapies to, right? So in a way, us finding this other virus, it being more severe, is probably more beneficial for us to find a potential therapeutic and to understand the severe form of the disease. So again, during the lockdown, I was talking to a lot of people at Lumina. I said, hey, you've got data in there. You got SARS-CoV-2 or SARS-CoV data. We should do something about that. So what they did is they actually, this was work from Joe Delaney and Jim Flynn at Illumina, and they put together a community group, and they kind of correlated all the coronavirus studies they could find. And basically they allowed researchers that were working on the virus to access their database for free, which I thought was really cool. Again, what we're looking at is the SARS-CoV-1. This is where we drew our data from. Again, it was in 2002. There's been studies on it. What we found, there was some monkeys, a few human, but the majority of these studies were done on mice. So what we decided is, all right, let's use the mouse studies. And what we're going to do is look at lung tissue. Okay. So, which brings the question, mouse versus human. Obviously we're not using the organism, that we really care about, but I do think the mouse has a lot of advantages over the human model, especially in this case, in that you can control the variables. And I think what's very hard when you're doing or analyzing infection data is that with humans, they just kind of come into the clinic and then you get them then, right? You don't know when they were absolutely infected. There's no specific starting date, but with mice, we can control that. We can say they were infected at this time, and then we can see what that progression of that virus is, knowing that we have a definitive time when they were infected. Also, with mice, we can actually look at lung tissue. In that, with humans, if there's no way you're going to have a sick person that's going to agree for you to take lung tissue from them while they're sick. So with mice, it gives us an opportunity to say study the actual organ that's infected. They're cheaper studies than humans, and they are genetically identical. So that kind of removes some of the variation there. With the humans, you're obviously working on the target organism you care about, which is more relevant. If you work on humans, you don't have to kill mice, and you actually a lot of times will work on the actual target virus. Some of the cons of that, mice are different. The key is will the mice respond to the virus in such a way that it's applicable to humans? And then, these mice are genetically identical. Maybe this is too similar. We have, people vary. And also, a lot of times in order to find the human equivalent of the virus, you have to alter it a little bit to infect mice. So sometimes you do have to change the strain of the virus. And, with humans, though, some of the cons, people are different. They live different lifestyles, very expensive studies, and typically you only get limited samples. So we decided, again, the data I'm going to talk about is with SARS-CoV-1, and this is from mouse studies looking at mouse lung.